Right.
Okay, so this is from the 2009 paper. This is there's two ways we can solve this question. We can solve this question using the three-force method, or we can just solve it using moments. Now, if we were to solve it with the three-force method, we know this force here, we've been told that the force is going in this vertical direction. So if we do that, we can go up until we find the point where these two forces meet, right? We're going to call that the point of concurrency. Because there's only three forces in this diagram, now you might say, well, where's the third force? The third force is the reaction at this triangle. We should always expect a reaction at a triangle. So if we have a third force here, we know that that angle will be coming through and we'll have a reaction going in this direction. Now once I have those three lines, I can do a force polygon. If this one's going that way, if this one is going clockwise, they all have to be going clockwise. Yeah? So if this one's going clockwise, they all have to be going clockwise. So this one here is going to be pulling down, this one here is going to be pushing up. Now, another way of looking at this, right, is that if we know that if we're rotating around our pin, if this force, if we turn in that direction, we're going to go clockwise. Yeah? So if we're going clockwise, in order for that to balance, the other force has to be going anti-clockwise, which means this has to be pushing the bracket up. Now, sometimes it might not look like that, it might not make a lot of sense that it's pushing backwards, but that is the fundamental thing that matters. Is that if the only other force you have is turning the pin clockwise, then the reaction, whatever this force is here, has to be pushing it the other direction. Now sometimes that might be counterintuitive, but that's the answer that we're always going to go with. Now, we can use the three-force method, right? We can find the point of concurrency. Once we know the angles, we can draw a force polygon. But that seems to be very uncommon that people want to do that, even though it is very commonly asked in the preliminary exam. What we're going to do is we're going to solve this question instead just by using the moments method. Right, we know we can now tell which way our things are going, but we're just going to solve it using the moments method. So what we're going to say is, we're going to call this pin, we're going to call that the pivot point there, we're going to call that point P. So what we're going to say is, well, first of all, we're going to measure everything as clockwise as positive, and we're going to turn the sum of our moments about point P equals 0. That's what we're saying is our true statement that we know to start off with. Now, there's two other statements we have as well. We have the sum of the forces vertically have to equal 0, and the sum of the forces horizontally have to equal 0. But we're going to worry about moments to start off with. Now the reason why we like moments is that we can then ignore anything that's happening at point P. Because anything that's happening at point P, the distance, the perpendicular distance to point P is 0. I want to remind you that the definition, the formula for moment is moment equals force times distance, and I want you to remember that's the perpendicular distance. Always the perpendicular distance. That's really important. I don't know if that showed up. Yep. It always has to be perpendicular distance. So this distance here, 63, is that perpendicular to this force?
No.
No. So what we need to look at instead is we need to look at, if we extend this line out forever, at what distance will it be when it's perpendicular? We're looking at that distance. That's the distance we're interested in. Yeah? That's the distance we're interested in. That is our perpendicular distance. Right? But we don't have to solve it that way. We don't have to solve it that way. We could do it that way. We could figure out the perpendicular distance, but we're not going to solve it that way. Instead, we're just going to convert our force. We're going to convert our force into its horizontal and vertical components, and then we can use the dimensions that we've been given. Let's rewrite 63, showing that up a little bit. Okay. So, what I'm going to do is I'm going to eliminate this arrow here. It's no longer exists. Instead, I'm going to break it into two arrows. So where that was 100 or 10 newtons, now we're going to break that 10 newtons, and I'm going to do that here. Hopefully that's still in line. 10 newtons, we're going to break that up into a horizontal and vertical component. So this is adjacent, so it's going to be 10 cos 35 degrees. And this one here is going to be 10 sine 35 degrees. Can anyone tell me what those values are? I can take rough guesses. This will be about 8. 8.12, sorry, 8.19, and this one here, 5.74. Okay, so we're going to convert those two as these forces here. 5.74 newtons and 8.12 newtons. Does anyone have a problem with breaking those forces up into its components? No, we're good. We've understood that. Okay, so now what we're going to do is we've got our force here. We're going to, what did they call that? We're just going to label that letter F. So we have a way of referring to that. Okay, we're going to say all of these forces, we've got 1, 2, 3, 4. We're going to call this one here reaction at the pin, or RP. Okay, so we've got 1, 2, 3, 4 forces. We used to have 3 forces, but now we've converted this into 2 forces, so we've now got 4 forces. Yeah, we split that one, we now have 4 forces total. So we're going to write a formula here which has 4 forces times 4 perpendicular distances. Let's start with this one here. 5.74, and how far away is its perpendicular distance from the pin? A little bit of a clue for people there.
63.
No. This line, this arrow, how far away is it? It's 0. It passes through the pin. So we can just multiply that by 0. Okay, this one here, I'm writing a negative sign first. 8.19. Now, how far away is it from the pin?
What's it? 63.
63 is its perpendicular distance. Now, we can use everything in newtons and millimeters, but as long as we're consistent, it will actually, they'll divide out and we don't need to worry. So for the moment, I'm going to stick with millimeters. Okay, we've got this force here, RP. Oh, wait. Before we move on, is this going clockwise or anti-clockwise? So I'm going to turn the force, put my finger on the pin.
Positive.
So it's going positive. So I'm going to turn that into a positive. I always write negative and then turn it into positive, because negatives turn into positives, not the other way around. Not so easy. Okay, so I have reaction at P. What is the perpendicular distance from the reaction at P? How far away is that reaction from point P? It's a reaction that's
35.
passing through there.
Oh no, not that.
This reaction is passing through point P.
That's that line.
What is perpendicular? How far away is it from point P?
0.
0. Great. And then finally we have F minus F. How far away is F?
35.
35. Now, we've made an assumption that it is going up. We've made an assumption. We've said that it's going up, so we're going to put our finger on our axle, right, which is point P. We're measuring from point P, so that's our axle, is point P, because we said it's point P. And we're going to push in the direction of our arrow that we made an assumption. Which way are we going? Anti-clockwise. So we leave that as negative. So what I'm going to write here is I'm going to say,
RPB plus.
assume negative because it's anti-clockwise. Now, someone said, wouldn't something be plus? RP, would it be plus?
Yeah.
Okay, RP, is it clockwise or anti-clockwise of P?
Nothing.
Nothing. It's neither clockwise nor anti-clockwise. It passes through P. So it's neither clockwise nor anti-clockwise. Which means, straight away we can just ignore that and ignore that, because anything times 0 is 0. So what are we going to have? We're going to put this over the other side, so we're going to say 35F equals, and then I'm going to do the calculation. .97, and then that means that F equals, so dividing the number by 35 equals 14.74 newtons, right? The direction is straight up, and the answer was positive, so it's positive, therefore our assumption was okay. Yeah? We made an assumption that was going up. The assumption was positive, our calculation was positive, therefore our assumption was okay. Now, that's how we get F. Right? Not a huge amount of work to get F. Right? We had to convert that force into its horizontal and vertical components, and we had to do a simple moment equation. Now, to find RP, what we need to do is we need to do the sum of the forces both horizontally and vertically, and then we need to combine those forces to find out the resultant and the angle. Okay, so first of all, our sum of our forces horizontally. Okay, I'm setting to the right as positive. How many forces have I got? Well, I've got this one here, 8.19, and I've got the horizontal reaction for P. That's all I've got. Are there any other forces that I'm missing? No. Right? So that means that RPH equals, or the horizontal component of the reaction at point P has to equal 8.19. Okay? So what about our vertical forces? The sum of the forces vertically equals 0. Okay, well, let's have a look. We've got 5.74. We've got 14.74. And we obviously have to have something to balance those two. We've got that pushing up, that pushing up. The only thing that can push down is our R, the reaction at our point P, and the vertical, which is going to equal those two numbers together. Which is 20.48 newtons. Now, that only gives us the components, right? What we now need to do is we now need to take those components. We have the horizontal and vertical components, so this is 20.48, and this is 8.19. So what's that value going to equal?
Square root of both.
Yeah.
RP is going to equal
How do you guys find the upwards arrow?
because we did this one here. Yeah.
Yeah.
Also, we made a prediction earlier, but yeah, this is okay. So that's squared. I'm not sure where that number is on my calculator. Plus. Hey. I just don't. Oh, there we go. 22 sounds about right. 22.1.
Yeah.
Now, what's the angle? Now, I always measure the angle off the horizontal. So the so theta equals tan to the -1, opposite over adjacent. Okay. So 20.48 divided by 8.19. So shift tan answer equals 68.2 degrees. That seems about right. Seems pretty
Yeah.
reasonable.
Why is theta in the bottom corner, not the top corner?
Because typically we always measure from the horizontal.
Oh.
Yeah, we can measure from the vertical as long as you indicate where you're measuring. I don't care. Yeah, but as long as you indicate, but typically we measure from the horizontal. That's just like a convention. Okay, so that is what you need to do for 6 marks. Now, you have 10 minutes for 6 marks, right? 6 marks, you have 10 minutes. Yep, 10.8 minutes. So, took me a lot longer than 10 minutes, but I was also explaining it and also I'm writing it in enormous font, right? For you guys, you should be prepared for this sort of question, that this is something that's likely to come up, and I've explained before that what you need to focus on is make sure that you're always using perpendicular distances. That is absolutely the key here, is make sure that you're always using perpendicular distances. We all good with that? Okay, great. I will turn that off.